Hi class. In this video, we're going to start from where we stopped last time, okay, which is question number 3. So madam will repeat again for these questions, and then please check your answer for question number 3 here. All right, so calculate the equilibrium constant for all species if there is 3 mole of your hydrogen gas and also 6 mole of the fluorine gas are placed into a 3-liter container. Okay, so you can see over here we have our 3-liter container. So this value will be your initial concentrations, whereby you need to calculate using number of mole divided by the volume. So over here you can see the initial number of mole for the hydrogen is 1.0 molar. For fluorine is 2.0 molar. Okay, so using your reaction table or ICE table, so we are going to fill in this information. So hydrogen gas over here, we got 1.0 molar. For fluorine gas, 2.0 molar. Initial concentrations for HF equals to 0. Then in the second row, we have the change in concentrations. So following your stoichiometry ratio, so you look at each of the species, okay, but of course you need to make sure your equations is balanced. So the stoichiometry ratio for the hydrogens is 1. Therefore, for the reactor, we will minus 1x. For fluorine as well, because reactor will decrease over time, so negative or minus 1x as well. Hydrogen fluoride is your product, so product will increase over time, so we have a positive sign, meaning your concentration will increase with time. And that is the stoichiometric coefficients of 2. Therefore, you're going to add 2x. So over here, you just need to add them up together. 1.0 add negative x. So over here, you will have 1.0 minus x. For fluorine, 2.0 minus x. And for the HF equals to 2x. Right, so if you want to identify the equilibrium concentration of each of the species here, we have to figure out what is your value of x. So from here, we can write out the Kc expression using the balance equation. We have the product on the top, so concentrations of HF raised to the power of 2. Okay, and then over your concentrations of reactant H2 raised to the power of 1. And F2 also raised to the power of 1. So in this case, you just need to fill in what we have got at the equilibrium here. Okay, so equilibrium concentrations is what we are highlighting here. Okay, and then fill in the blanks. For hydrogen fluoride, 2x squared. For H2, we have 1.0 minus x. For F2, we have 2.0 minus x. And the value of Kc is given in the questions. 1.15 times 10 to the power of 2 give you 115. And let's do some quadratic calculation. So remember, 2x in the bracket, we need to open up the bracket. So 2 squared give you 4, and we have x squared. And then open up the brackets over here, give you 2 minus 3x plus x squared. So this one is the quadratic calculation. You need to utilize your mathematic skills to do these calculations. Okay, so after you solve the quadratic equations, you will get this 2 value of your x. So first one is 2.1397. And the second value of x is 0.19684. Alright, so our final target is the equilibrium concentration. So you must make sure that equilibrium value should be always positive. So you need to try and error, substitute the value of x into the equilibrium concentration. So say for example, if I want to calculate for the concentrations of H2. Okay, if we're using the value x equals to 2.1397, it will give you a negative value for the concentration, which is wrong. You cannot, the concentrations cannot be a negative value. Therefore, we will say the first value of x, that one with 2.1397, is not valid. So we can ignore the value of the x. And then let's try for the second value, 0.9684. So calculate for the equilibrium concentrations of the hydrogen. 1.0 minus the value of x. So say in this time we use the value of x 0.9684, which will give you the concentration 0.0316 molar. So you get a positive value for the concentrations. That means this is your answer. Okay, and then carry on with the concentrations of our fluorine gas at equilibrium. 2.0 minus x, same value of the x that we are using, give you 1.0316 molar. And finally, we have the concentrations of the HF at equilibrium, which is equals to 2x. So substitute the value of the x, and you will get the answer 1.937 molar. So in this case, the questions ask for the equilibrium concentrations of all species, and here is your answer, which is highlighted in green color. So the next topic in chapter 6.2, equilibrium constant, we want to look at the degree of dissociation, which is represented by the symbol alpha. Okay, so the degree of dissociations refer to a certain fractions of molecule which have been dissociated or decomposed into smaller molecules, ions, or atoms. Or it can also refer to the amount of substance that have been used or has been reacted in a particular chemical reaction. So the formula is alpha equals to change in concentrations of a reactant over the initial concentrations of a reactant. Or in short, the formula can be written this way. Alpha equals to the change in concentration over the initial concentration if you want to use the formula or the symbol of concentration. Okay, so apply the same concept you're using previously. Let's look at question number 1. If 0.024 mole of the N2O4 is allowed to reach equilibrium with NO2 in a 0.372 liter flask at 25 degrees Celsius, calculate the degree of dissociations of N2O4. That means if you look at this sentence, the sentence says is allowed to reach equilibrium. That means the reaction is not yet started, which means this 0.024 mole is the initial number of mole. So we can calculate first for the concentration of this N2O4 at initial. So equals to 0.024 divided by 0.372 liter. Please make sure you check the unit. Volume must be in liter if you're using this formula. And the concentrations will be 0.0645 molar. Alright, and then let's fill into your ice table. So initial concentration 0.0645 molar. Okay, with nothing for the NO2. So since these equations have already balanced, so the change in concentrations is negative x for the reactant. And for the product, according to the coefficient, okay, we need to plus 2x. So 0.0645 minus x, and then over here you have your 2x. In order to find the value of x, if you refer back to the questions give you the value of Kc. Okay, so that means you need to write the Kc expressions, and from the value of Kc, you need to figure out what is the value of your x. Right, so let's try to calculate the value of our x. So Kc, according to this equation, we have the Kc expressions. NO2 concentration raised to the power of 2 over N2O4 concentration. So the value of x, 4.61 times 10 to the power of -3. Then we have 2x in the bracket to the power of 2, and we have 0.0645 minus x. And over here, you need to solve the quadratic equation. Alright, over here, after you solving your quadratic equation, you will get two value of x, and you need to try and error to substitute the value of x into your equilibrium concentrations. If let's say you get a negative answer, negative concentrations, then that will be wrong. Okay, because your concentration should always be positive value. Okay, so in this case, the value of x value over here, we have to ignore it. So we are using only the x value, which is equal to the first one. Alright, so back to the questions. To calculate degree of dissociations of N2O4, so we come up with the formula. Degree of dissociations equals to the change in concentration of N2O4 over its initial concentration. So in this case, the change in concentrations equals to the value of x, and the initial concentrations 0.0645. The negative signs of this negative x you don't have to put in here, because negative indicate that reactant concentration will decrease over time. So to calculate for the alpha, degree of dissociation, you don't have to put the negative sign. Okay, so let's calculate for this one. 8.064 times 10 to the power of -3 divided by 0.0645. And the degree of dissociations equals to 0.125. There is no unit for degree of dissociation. So if let's say you want to calculate the percentage of dissociation, don't worry, you just times with 100%. So here's the answer for question number 1 here. Let's proceed to second questions. Consider the decompositions of hydrogen bromide Hbr in the following equation. And in these questions, you are given also a balanced chemical equation. So initially, there is 1.0 mole of Hbr, which is placed into a 2.0 liter flask. There's a missing unit over here. Please record down the unit for volume, 2.0 liter. Is allowed to reach equilibrium. Next information is very important. It says that at equilibrium, the concentrations of H2 is 0.15 molar. So you are given one value initially and another value at equilibrium. And the questions ask to calculate the degree of dissociations of Hbr. So first of all, we need to calculate the concentrations of Hbr initially. So initial concentrations of Hbr, we have using 1.0 mole divided by 2.0 liter, which gives you 0.5 molar. So in your ice table, again, we want to use the ice table because you have your initial concentration, you have your equilibrium concentration. So put in your balance equation into the table. So 2 Hbr gas in equilibrium to 1 mole of hydrogen gas and also 1 mole of the bromine gas. So in this case, you only have the initial concentrations of Hbr, so 0.5. And the concentrations for H2 and also Br2 are both 0 because the reactions is not yet happened. So no concentrations for the product. So when the reaction starts, your reactant Hbr will decrease over time. Okay, so according to the balance equation, the change in concentrations for our reactant Hbr, we minus 2x due to the stoichiometry ratio. And for the product H2 and Br2, we need to add 1 value of x. And for bromine, also add 1 x. So at equilibrium for Hbr 0.5 minus 2x. For H2 we have x, and for Br2 also we have x. So in the question, it says that at equilibrium, concentrations of H2 equals to 0.15 molar, which means the X values is also equals to 0.15. So if you fill in the blanks over here, you will see X equals to 0.15. So now you have figured out the value of X. Next, we want to calculate the degree of dissociations of Hbr. So degree of dissociations formula is equals to the change in concentration. In this case, we want to find change in Hbr over the initial concentrations of Hbr. So fill in your value. Change in concentration Hbr equals to 2x. Again, ignore you don't have to put in the negative sign. Okay, so 2x over Hbr initially is 0.5. So substitute your value of x into the formula. So 2 times 0.15 over 0.5. And it gives you the value of degree of dissociation 0.6. So you can see over here the change in concentration Hbr, which means we refer to the row over here. So for Hbr, we only take notes on the value of here, 2x. Alright, so next we proceed to question number 3. Question number 3 with a slight challenge because the questions give you the percentage of degree of dissociation and you need to solve another problem. So the questions say that the formations of phosphorus pentachloride PCl5 is given as follow. So the equations given is already balanced. If 3 moles of PCl3 and 2 moles of Cl2 are allowed to react at 200 degrees Celsius, 72% of chlorine was completely reacted when the system achieved equilibrium. Then, calculate the percentage of PCl5 formed at equilibrium. So in these questions, you are given the starting material, the number of mole, and the 72% of chlorine which was completely reacted, and this percentage refer to the percentage of degree of dissociation. So let's just fill in the ice table. So if the questions only give you a number of mole, you can either choose whether you want to convert into the concentrations, which you need to assume the concentrations equals to 1. Otherwise, you can just follow and keep the ice tables using number of mole. So let's fill in the informations in the ice table. So PCl5, we have 3 mole initially. Chlorine, we have 2 mole initially. And PCl5, the product, don't have anything. And then the change in number of mole for PCl3, this one is still the same according to the balance equation. So for PCl3, you minus 1x. Cl2, you're going to minus 1x. PCl5 as the product, the number of mole also will increase over time. So we need to plus 1x. So the number of mole at equilibrium, we have 3 minus x for PCl3. For chlorine, we have 2 minus x. And for PCl5, you have only 1x. Alright, since the questions give you the percentage of dissociation, 72% of chlorine, so we try to write out the formula for the percentage of dissociation. Okay, so in the formula, we know that we need to use the change in concentration. But since in the ice table, you are using number of mole, therefore we're using the change in number of mole for chlorine over the initial number of mole for chlorine, and then times with 100%. Okay, so fill in the values over here. We have 72% equals to the change in number of mole. We are using the values for the chlorine, which is only 1x. Okay, so x over the initial number of mole for chlorine, which is equals to 2 times with 100%. So the x values over here is equals to 1.44. mole. So now you have already found the value of x. Then we try to figure out what is the value for the number of mole at equilibrium. Okay, and then you try to substitute the value of 1.44 into each of the equilibrium number of mole here. So 3 minus 1.44 for PCl3, it gives you the values of 1.56 mole. And for chlorine, 2 minus 1.44 gives you the value of 0.56. And last one, the number of mole at equilibrium for PCl5 equals to 1.44 mole. Alright, so come to our target of the questions to find the percentage of PCl formed at equilibrium. So if you still remember from chapter 1, if you want to find the percentage of a species form, you need to figure out what is the mass. So this is kind of like a percentage mass from our chapter 1, percentage mass, percentage of the PCl form. And you're using the mass form at equilibrium. So in order to find the percentage of PCl5 form, we need to figure out the mass of PCl3, Cl2, and PCl5 using the number of mole we have calculated at equilibrium. Alright, so for the mass of PCl3, okay, using the number of mole 1.56 times with its molar mass 137.5, it gives you the values of 214.5 gram. And then for the mass of chlorine, using the number of mole at equilibrium 0.56 times 71 gram per mole, you got 39.76 gram. And for the mass of PCl5 form, using the number of mole 1.44 times with its molar mass 208.5, and it gives you the value of 300.24 gram. So using all of the mass of this species, we need to calculate the percentage of PCl form at equilibrium. Alright, so finally, percentage of PCl5 form equals to the mass of PCl5 over the total value of the mass. So mass of PCl3 plus the mass of Cl2 plus the mass of PCl5 times with 100. And the final answer gives you 54.15%. Alright, so this is the working steps for our question number 3. So for the ice table over here, ice table, remember we can use any of the quantity. The quantity over here refer to either you have concentration, you have partial pressure, or in this case, we are using number of mole. Alright, and then for the percentage of PCl5 form, this one is, it will refer to your chapter 1, which is related to percentage by mass. This chapter 6.2, it involves quite a number of calculations, so you must practice about the working steps. How to draw the ice table, how to calculate for the value of x, how to come up with your Kc or Kp expression, and etc. Alright, so here is a list of exercise 2 for you to do some practice, and please attempt the questions prior to question 1, question 4, question 9. So if you have any questions, please let me know for further discussion. So that's it for this video. Thank you.